This presentation is about how to analyze Quicksort. So Quicksort is one of the fastest, most popular algorithms for sorting n numbers. So we will start by defining the algorithm and give some intuition, and then we'll continue with its analysis. So it's based on the divide and conquer paradigm, which is a paradigm for designing algorithms. So this means that we start with a whole instance, and then we see it's too big for us to sort immediately. So we divide it into smaller instances, and then we recursively sort these instances to get a solution to the whole problem. To define our quicksort algorithm, we need to have 3 steps, like how do we select, how do we divide the numbers, then how do we recursively sort them, and then how do we combine our solutions. So given n numbers, a1 to a2 to an, we proceed as follows. So in 3 steps. So here I will also have a small example. So we have a bag of numbers. Okay, so maybe we have the numbers 7, we have 5, 6, 2, 4, 3, 1. So it's the input contains 7 numbers, and that we want to sort. So we're given a bag of numbers. So here this is a1 to an. So now in the first step, our algorithm will select a random pivot among the given number. This will be useful to divide our instance. So select a random pivot AP. This would be, for example, 4. That could be our random pivot we selected. So this will be used to partition our instance into smaller instances that we can solve recursively. In the second step of our algorithm, we will use this pivot to partition our data into all the numbers that are smaller than our pivot and all the numbers that are bigger than our pivot. So we let S be the set of numbers such that they are smaller than the pivot, and L would be the set of numbers such that they are bigger than the pivot. So in the example, this will give us the set S, that elements that are smaller than the pivot will be 2, there will be 3, there will be 1. And the set L, that is larger than the pivot, will be 6, 7, and 5. So this, we selected a pivot, now we got 2 smaller instances. The instance consisting of all the smaller numbers than the pivot, the set S, and the set L consisting of all the numbers that are bigger than the pivot. Of course, this has not sorted up the whole instance, so what we need to do in the final step of our algorithm is to recursively sort the smaller instances. So once we have sorted S and L, then we have the whole input sorted. Okay, so this means that we recursively continue here. So maybe here we select 2 as a pivot, then we get 2 smaller instances, 1 and 3. Well, then we are happy. It's easy to sort a single number. And here maybe we're lucky and select a 6 as a pivot, and we got the sub-instances 5 and 7. And we're happy because this is single numbers that are easy to sort. So now you can see that the sorted sequence is now obtained by reading this from left to right, inserting the pivots at the right place. So here we have 1, then we have the pivot 2, then we have 3, we insert the pivot 4, and then 5, pivot 6, and last 7. So we got the sorted sequence. So that's the quicksort algorithm. So we are given a bag of numbers, or n numbers. We select a random pivot AP in the first step. This partitions the data into 2 sets. The input that is smaller than the pivot and the input that is larger than the pivot. And then we recursively sort these 2 smaller instances to get a sorted sequence of the input. So to analyze the quicksort algorithm, we can observe the first step, selecting a random pivot, that we can do very efficiently. Just select a random number between 1 and n. However, after we selected a random pivot, we need to partition the current instance into 2 smaller instances, namely S and L. And to do that, we need to compare each element to the pivot. For example, look at the example we have here. We select the 4 as a pivot. Then we will start comparing the numbers with our pivots. We compare 6 with 4. We see that 6 is bigger than 4, so we put 6 in L. Then we compare, for example, 2 with 4. We see that 2 is smaller than 4. We put it in S, and so on. So this means that we need to compare each element in this bag with a pivot. So in this example, we will make 6 comparisons, okay, in the topmost bucket. And then when we recurse here down here, we will make 2 comparisons, and here we will make 2 comparisons. So in this case, the total number of comparisons we will make is equal to 10. The important observation is that the running time is proportional to the number of comparisons we make. So to analyze the running time, we really need to understand how many comparisons does the quicksort algorithm do in order to partition the data. So in this example, we make a total of 10 comparisons. So the running time of this example will be proportional to 10. So to do this, let's first consider the worst case running time, and then we'll see that selecting a pivot at random will greatly improve the running time on expectation. So now we would like to understand the worst case running time of quicksort. So suppose for simplicity that our instance is just a bag of numbers that are already sorted. So we have A1 to A2 going up to AN. Okay, and we wish to sort them using our quicksort algorithm. Now we are very unlucky in our choice of pivots. So the first pivot we choose is AN. So why is this bad? Because this will result in that our instance L, the set of numbers that are bigger than a pivot, is empty. There is no such number. And there is n minus 1 numbers that is smaller than the pivot n. So we made a lot of work in order to get an instance consisting of only one less number. In particular, we did n minus 1 comparisons here. So this was an unlucky choice of pivot. And again, we might be unlucky if we pick the last element as a pivot. So now we do n minus 2 comparisons, and all we get is an instance consisting, an identical instance almost, just consisting of n minus 2 numbers, a1, a2 to an minus 2. And then you continue in this manner all the way down. You're always unlucky picking the biggest element as a pivot. So here we pick a2, and then we get a1. So here we would do one comparison, one above we would do 2 comparisons. Here we do n minus 3 comparisons and so on. N minus 3, n minus 2, n minus 1. So we can see that the total number of comparisons, and remember that the number of comparisons was proportional to the running time, is equal to the sum of I from 1 to n minus 1 I is equal to n minus 1 times n over 2. So this exact equality is not important. What is important to notice is that this is proportional to n squared. And that's a bad running time. We want to have a much faster, close to linear time sorting algorithm. And this is far away from linear. This is quadratic time. So this shows that worst case running time of quicksort is not good. So if you're unlucky in the choice of pivots, you can have a bad running time. However, we will show that when we select the pivot at random, this is very unlikely to happen, and in fact the expected running time is very good. Because it's very unlikely that you always select the last or the biggest element as your pivot. So in order to analyze the expected running time of quicksort, we need some notations. We let zi be ith smallest element in input, and we let xij be equal to the indicator variable, so be the random indicator variable defined by x of ij is equal to 1 if zi and zj were compared, and 0 otherwise. So xij is a random indicator variable that we define to be equal to 1 if we compare the ith smallest number to the jth smallest number during the execution of the algorithm, and 0 otherwise. This is a random variable since we select the pivots at random, and which elements will be compared depends on which pivots we selected. So the reason that we introduced these random indicator variables is to be able to write the total number of comparisons, so the number of comparisons, in a nice way. So now we can write the number of comparisons to be equal to the sum over all pairs ij, xij. And moreover, we can write the expected number of comparisons, which is proportional to the expected running time, as just the expectation, or by definition, the sum of ij, xij. And then you can do linearity for excitation to move inside in the expectation inside the sum. So we get the sum of all pairs expected xij. So the goal now becomes to understand how can we analyze the expectation of the indicator variable xij. So we need to understand the expectation of the indicator random indicator of xij. Well, first of all, this takes value 1 if and only if I smallest number is compared to j smallest number and 0 otherwise. So this is simply equal to the probability that Zi and Zj are compared. So now we want to analyze what's the probability during the execution of Quicksort that we compare the I smallest number with the j smallest number. We have the following claim, which is the key to the analysis. So probability that Zi and Zj are compared is actually equal to 2 over j minus I plus 1. And this follows from the observation that Zi and Zj are compared if and only if the first element selected as a pivot among the elements in the set Zi plus 1 to Zj minus 1 Zj is either Zi or Zj. Okay, so what I'm saying is that Zi and Zj are compared if and only if whenever we select a pivot among the elements Zi to Zi plus 1 to Zj is either Zi or Zj. So if you believe in this observation, then the claim follows rather immediately, because remember we select a random number as our pivot. So now consider a case when we select an element as pivot among the set Zi to Zj. Then there are two outcomes that make us compare Zi and Zj, namely either we select Zi or we select Zj. However, how many outcomes are there in total? Well, if you count the total number of elements in the set, they're exactly j minus I plus 1. So the probability that we would either select Zi or Zj is exactly 2 over the number of elements in the set, which is j minus I plus 1. However, why should you believe in this observation? So let me explain why this observation is true. Alright, so now in order to convince ourselves that this observation is true, first notice that in the beginning all the elements from the set Zi to Zj are in the same bucket. So in the beginning we have some smaller elements than Zi and all the guys to Zj are in the same bucket, and we have some bigger elements than Zj. Now if we select a pivot that is smaller than Zi, well then all these elements will go to the bucket that consists to the instance L with larger numbers. And if we select a pivot that is larger than Zj, then by the same argument Zi to Zj will be in the same subinstance S. So by this we can see that if we select a pivot that is not in between Zi to Zj, these numbers are not affected in the sense that they are still in the same subinstance. Now consider the situation when it's the first time we select a pivot in between Zi and Zj or one of Zi and Zj. Now suppose this pivot is actually in between Zi and Zj. Then I claim that I smallest number will never be compared with the j smallest number. Because in this case we will send Zi to the smaller bucket and we will send Zj to the larger bucket, and from there on we will treat these two instances as independent. So I and j will never be compared. So the only chance for I and j, Zi and Zj to be compared is that we either select here either Zi or Zj as a pivot. If that happens, then we will indeed compare them, because if Zi is, for example, the pivot, we will compare all these elements with Zi to know in which smaller subinstance it is. So I think this gave us the explanation why this observation is true. So to repeat, if we select a pivot that is not in the interval between Zi and Zj, then all the numbers between Zi and Zj are still in the same subinstance. And now consider the case when it's the first time we select a pivot in between Zi and Zj. If this pivot is strictly in between Zi and Zj, then we split Zi and Zj into independent instances. However, if the pivot is either Zi or Zj, then they will indeed be compared. However, this happens only with probability 2 over the number of elements in between the interval, which is j minus I plus 1. So that's why the claim follows. Alright, so now remember that we are interested in analyzing the expected number of comparisons, and we now understand what the probability of comparing the I smallest to the j smallest is. So now we simply have that the expected number of comparisons is equal, by summing up of all the pairs, the probability that this I smallest element was compared with j smallest element, but by the previous claim that we proved, this is exactly equal to 2 over j minus I plus 1. So now in order to understand the number of comparisons and thereby the running time, we have to understand this expression. So this is by simple rewriting. I just write first sum over I from 1 to n minus 1, and then the sum over j that is bigger than I, so from I plus 1 to n, 2 over j minus I plus 1. Now I can lift out the 2, so I can write the 2 in the beginning of this expression, and here I get the 1. Then I can also change the index over this sum here, from I plus 1 to n. Instead I can sum over index L that is equal to j minus I. So here I will get that the 2 times the sum of I from n minus 1, sum of L from 1 to n minus I, 1 over L plus 1. But this we can now upper bound by replacing this here by simply L. That will only make it bigger. And we can sum from 1 to n. So instead of summing from 1 to n minus I allow ourselves to sum from 1 to n. That can only make it bigger. So this is at most 2 times the sum of I from 1 to n minus 1, the sum of L from 1 to n, 1 over L. But now I think you recognize this sum. So this is nothing but the nth harmonic number. So that's equal to the nth harmonic number. And we sum the nth harmonic number n minus 1 times. So it's at most 2 times n times h of n. And this is roughly equal actually to 2 times n ln n, so the natural logarithm in n, which is equal to theta n ln n. So this shows that the expected number of comparisons is actually only n log n, compared to the worst case that was n squared, and therefore the expected running time is n log n, which is actually the optimal running time we can achieve with a comparison-based sorting algorithm. So the main ideas was to realize that the running time is related to the number of comparisons, actually proportional to the number of comparisons, then use random indicator variables to count the number of comparisons. So once we realize that the probability that I smallest number is compared to the j smallest number is 2 over j minus I plus 1, then the last part here follows by simple calculations.